Hello, welcome to this presentation on digital signal processing on band limited signals and their sampling. In this lecture, we are going to look at how you can sample the so-called band limited signals to obtain discrete time signals and what the conditions are for you to be able to reproduce the original continuous time band limited signal back from the sampled one. So let's get some intuition on band limited signals. The word itself suggests that band limited signals are limited in the range of frequencies that they possess. So that is, they have a finite set of frequencies and they are restricted. To get some intuition on band limited signals, let's get the first one out of the way. Generally, band limited implies time unlimited. Why is this the case? So if you see the notes or if you've seen the previous lecture, remember, a time limited signal can be thought of as any time limited signal multiplied by the rectangular pulse. If that signal were band limited also, then if you convolve it with the Fourier transform of the rectangle, which is a sink, you can show that it becomes band unlimited. So band limited implies time unlimited, time limited implies band unlimited. So this is something which you can keep in mind. But more importantly, signals that have very gradual movements, very gradual, not very high slopes, and which change very slowly, generally tend to have a lesser set of frequencies. But signals which have abrupt movements, discontinuities, or even points of inflection, or points of discontinuity, these signals tend to have a higher frequency content. Why is this the case? So this is something I'd like you to think about, but whenever there are abrupt changes from continuous behavior, sinusoids are not good candidates to approximate these, and in fact, if you remember what you've seen in signal systems about the impulse function, an infinite number of frequencies are required to produce sharp transitions. Okay, fine, but then in practice, what is the issue which we face? Okay, we said for example that all band limited signals are time unlimited, which means that they stretch from minus infinity to infinity in the time domain. Does this mean that we cannot perform any processing? No, that's not the case. Since this is an engineering application, approximately band limited is good enough for many applications. For example, if you take the rectangular pulse in time domain, the Fourier transform is the sink. Now you could argue that the sink is actually band unlimited, meaning that the sink stretches from minus infinity to infinity in the frequency domain. But remember that the sink decays as 1 by f, which means that if you take a high enough frequency, then you can approximate the Fourier transform as that being that of the rect. Of course, you will lose some information, and the more information that the higher the frequency that you choose to retain, the closer an approximation of the rectangular pulse that it will be. This is something I want you to bear in mind. So yes, for engineering applications, we can get away with an approximately band limited situation. So we can handle band unlimited signals also to a great extent. The next keyword which I want you to remember is aliasing. So we saw, in the context of the wagon wheel, what aliasing is. Remember, whenever you have an issue while you sample, you will start getting wrong frequencies. So if you recall our wagon wheel example, we said that if you sample let's say the wagon wheel has a dot which moves in the clockwise direction. If you sample at more than twice the rate of rotation of the wheel, you will see the red dot moving in the correct direction. If you sample exactly at twice, remember that you only see two dots on the rim. But if you sample at less than twice, notice that even though the wheel is supposed to be moving clockwise, you see an anti-clockwise motion. Why? This is because the actual movement is being mapped to an incorrect frequency. Why does that happen? Because if you recall the way we imagined it, where we take a photograph and another photograph, by the time you took a photograph, the wheel moved more than halfway, and so for you it looked like the wheel is actually moving in the anti-clockwise direction, and in this particular case at 20% of the speed of the wheel. So 20% of the wheel rotation rate. This gives you an incorrect picture, and what happens is that the frequency which was originally present is said to have aliased, meaning has appeared in the incorrect location because you did not sample sufficiently fast. Generally, aliasing is accompanied with some loss of information. This. So there is loss in information, and this loss in information cannot really be made up for. I mean, there's no real way to make up for it. So this is something you should bear in mind, but there are some exceptional situations where you can undo it, but you need some additional information. So in general, if you do not sample a signal at more than twice the maximum frequency present in it, you will encounter aliasing. So now if you look at what the Nyquist criterion is, in the notes we have a more precise definition, but it's not difficult for you to see that whenever we sample at more than twice the maximum bandwidth of the signal, you will not get aliasing. If you want a more kind of visual representation, if you look at this particular picture, I'm just going to pause it and maybe make an explanation. This is actually at the threshold. We have a signal, a continuous time signal which is sampled. Its extent is between -w and w, so its baseband bandwidth is w, and it spreads between -w and w. If you sample at fs, which is 1 by t, if this fs exceeds 2w, because see, this is w, this is w, then you can capture the signal in the discrete time domain without this triangle interfering with this one. If you choose fs to be any larger, that only makes it better, meaning it spreads further and further. And why is this advantageous? Because you can see that there is this triangle over here, and there is potentially a way to get just this triangle out and remove all these other triangles. That is called reconstruction, without losing any information. But if you look at this situation, whenever your fs, which is 1 by t, is less than twice w, this triangle and this triangle are going to interfere with each other, and this red portion is actually aliased because the frequency appears in an incorrect location. Now this automatically tells us something. Only frequencies between -1/2t and 1/2t can be represented after sampling. Why is this the case? If you sample, maybe I'll just move the diagram a little bit again. If you sample, notice that this, I'll move it a little bit again. If you look at this particular point over here where my cursor is, this is 1/2t, this is -1/2t. Anything to the left of -1/2t, anything to the right of 1/2t is a repetition. So it's like the region which is present between -1/2t and 1/2t is duplicated again and again and again. Since that is what happens, we are able to consider only frequencies between -1/2t and 1/2t, which satisfies our intuition that if your signal itself has frequencies only between -1/2t and 1/2t, that is in this case w is less than 1/2t, we are in good shape. All other frequencies, if they are present, will get aliased. Okay. So when we talk about sampling sinusoids, this is one way to just reinforce our intuition. This is a 1 Hz sinusoid, as you can see. If t is measured in seconds, then it's a 1 Hz sinusoid. What should the sampling rate be for us to be able to faithfully reproduce this? Let us try using exactly 2 Hz. If it is exactly 2 Hertz, we sample at t is equal to 0, t is equal to half a second, t is equal to 1 second. What do you see with the red dots? The red dots are all 0, which means, of course, you don't need to think too much. The red dots being 0 means that the signal you actually sampled is 0. You have actually lost all the information. Can you connect this with the wagon wheel and try to find out what situation this corresponds to? Think about it. But over here we said 2 Hertz is not enough. What happens if we go to 2.1 Hertz? While our intuition doesn't really, it doesn't really tell us whether this is good enough, maths tells us that this is good enough. In fact, if you sample at 2.1 Hertz and have dots to the left and right, all of these dots, if you will satisfy the condition that there is a unique sinusoid that you can draw through this, and that is the sinusoid that is of 2.1 Hertz. Sorry, 0.1 Hertz. So anything greater than 2 Hertz works. There are some advantages though of sampling at much more. For example, let's say we sample at 7.2 Hertz. You see that there are many more points and it's a denser situation of sampling. Now, it's not always a good idea to sample at a higher rate, but in several situations, system design becomes much easier because representing more samples of the signal may allow you to perform processing easier. Now, these are details which are implementation specific, but remember this comes at a cost because sometimes you're going to perform an analog to digital conversion, and this analog to digital conversion is actually a costly operation, especially when you perform at high speeds. So when you perform this ADCing at high speeds, it becomes a little bit of an issue because it consumes a lot of power and makes system design even more complicated. However, in some situations, having a richer digital representation allows you to visualize or process the signal in various ways with much more ease. So one question which we have is, okay, we do have a band limited signal. We have a band we don't have a band limited signal, but we want to perform sampling. What can I do? So one step which you should perform, or most situations demand, is that you have to remove the out of band content for sampling to be useful and to avoid the aliasing effects. How do you do that? So the way to do it is to use the so-called anti-aliasing. So what does this anti-aliasing entail? So in general, to begin with, we possess unnecessary content out of band. Sometimes your signal may be band limited, but there may be noise which is outside. For example, if you are building a communication system where your bandwidth of interest is, let's say, this particular chunk of 1 megahertz, your radio is going to pick up all the noise which is outside this 1 megahertz also. So it's very important for you to use a filter to remove the unnecessary content. Another name for this aspect of removing the part which is outside the bandwidth of interest so that you can sample correctly is called anti-aliasing, because it's actually designed to prevent aliasing of the out of band contents. So the way to do it is to typically keep a low pass filter which only retains the frequencies of interest. Here is an example. Let us say that you have X of f, which is a band unlimited signal. Now this band unlimited signal cannot be sampled without avoiding aliasing. So definitely the parts which are to the right, let me use a different color. Okay, these portions are going to alias back if you perform sampling. How do you avoid that? We can filter it using a low pass filter called an anti-aliasing filter, which is between -W and W. And then the remaining part of the signal can be sampled without any issues. You may say, what about this part? What about this part? Again, like I mentioned, these parts may or may not be interesting, but if you are able to sample only at between minus W and W, the question is, do you want to do anything at all, or say no, since my signal is band unlimited, I will give up? No. At least can you make some inference between minus W and W? Let's try that. Or what is worse, the parts where I've labeled a question mark, if they are only noise, it's even better. You can get rid of them before you perform the sampling. So if you perform this anti-aliasing, you are able to cut off this part. This could result in loss of information, or it could be good and you are actually just removing the noise, and then the remaining part of the signal can be passed through a sampler, which is basically an impulse train. So in the time domain you are multiplying by impulse train, in the frequency domain you convolve by impulse train, and these copies are going to result in non-overlapping. So the copies of this sampled, this black particular curve, will be non-overlapping, and you can then perform digital processing on it, which is going to be the focus of the remaining part of this course. One issue which is pending is, okay, we went from continuous time to digital, but then I have promised you that if you honor the Nyquist criterion, you can go back from discrete time to continuous time without any loss of information. How do we do that? So that is about reconstruction of continuous time signals, and that is going to be the topic of our next video. Thank you.